In my previous video, I discussed about geostrophic wind and what changes as we move upward that makes the wind become geostrophic. At the surface, the pressure gradient force tries to accelerate the air from high pressure to low pressure systems, shown by this mathematical relation, the balance equation. But the surface also exerts friction. For example, over a rough terrain, in this figure, friction is relatively strong. The wind speed is reduced and therefore Coriolis force is also reduced. Over a smoother surface, still we have friction, but it is weaker. The wind can become faster, so the Coriolis force becomes stronger. The pressure gradient force is no longer fully balanced by Coriolis, as we see in this equation. So the wind develops a component across the contours toward lower pressure system. Once we rise above the atmospheric boundary layer in the free atmosphere, the direct influence of surface friction becomes much smaller, and the horizontal acceleration and friction are nearly negligible in this formula. Now, two horizontal forces dominate, the pressure gradient force and Coriolis force. When these two forces balance, we obtain what we call the geostrophic wind. Now, let's write geostrophic balance mathematically at constant height and also at constant pressure surfaces here on. At a constant height, the horizontal pressure gradient force is determined by how pressure changes horizontal, shown by nabla sub zp, defined in this formula. The subscript z simply tells us that we stay at the same height. In geostrophic balance, which we have balance between pressure gradient force and Coriolis force, the pressure gradient force is exactly balanced by the Coriolis force, which depends on the Coriolis parameter F, the vertical unit K hat, and the horizontal geostrophic wind vector Vg. If we separate the wind into its east-west component Ug and north-south component Vg, we obtain these two simple expressions. They tell us that the geostrophic wind is determined by the horizontal pressure gradient at that height. The surface and upper atmosphere use different but equivalent views. Aloft, we usually fix pressure and map the height of that pressure surface as shown in this figure. In this north-south vertical cross-section, the 500 hectopascal surface is not flat. Its height changes with latitude, as you can see in this figure. To see why height can replace pressure in the geostrophic wind equation, consider pressure as a function of x, y, z. For the zonal wind, we take a north-south slice. And since we are using here the partial derivative of pressure and use change relation, then we don't have dx. Dx is 0. Therefore, the gradient term related to dx is dropped here. And because we move along the 500 hectopascal surface is a constant surface, therefore dp is also 0. Here we use another equation, which is hydrostatic balance equation given by this formula. This equation together with this representation combined together, we get our key transformation. A horizontal pressure gradient at constant height can be represented by the slope of a constant pressure surface. Substituting this relation into the geostrophic wind equation here gives us this governing equation for presenting the geostrophic wind at a constant pressure level. That's why upper air weather maps show geopotential contours based on this relationship. A closely spaced height contours mean a stronger height gradient, therefore a stronger pressure gradient force and a stronger geostrophic wind. We have now derived the mathematical relationship between the pressure or height gradient and the geostrophic wind, but meteorologists often need a much quicker way to interpret this relation. Bayes-Bellot's law gives us exactly that geometrical rule. The equation tells us that geostrophic wind flows parallel to the contours, with the pressure gradient force on one side and the Coriolis force on the other side. Bayes-Bellot's law is simply the practical geometrical consequence of this balance. In the northern hemisphere, if you stand with your back to the wind, this is wind, your back to the wind, lower pressure or lower geopotential height lies to your left and the higher pressure lies to your right. In the southern hemisphere, for example, it's the reverse. So, Bayes-Bellot's law is not a separate idea. It's simply geostrophic balance expressed as an easy rule for interpreting the wind direction. Are geostrophic winds always westerlies? No, geostrophic winds are not always eastward. Their direction depends on the arrangement of high and low pressure systems, or equivalently on the orientation of the pressure or height contours. In the northern hemisphere, geostrophic wind blows parallel to the contour, with low pressure on its left and high pressure on its right. In this example, the pressure pattern is arranged so that the geostrophic wind points northward. So, even though many mid-latitude winds are westerly, geostrophic wind itself can be northward, southward, eastward, or westward, depending on the pressure field. Where is geostrophic balance most relevant? They are more common in the mid-latitude. The key is the Rossby number given by this relation. It compares inertial acceleration with Coriolis acceleration given here, u divided by Coriolis parameter multiplied by L, which is the length scale. At the equator, F equals 0. F, the Coriolis parameter given by this relation, which phi shows latitude. So Coriolis cannot balance the pressure gradient force, and geostrophic balance therefore breaks down. As we move poleward, F increases, you can see in this figure, but there is a second important ingredient here. Mid-latitude weather systems are enormous, often around 1,000 kilometers or more. Large F together with large L makes Rossby number extremely small. When Rossby number is extremely small, less than 1, Earth rotation strongly constrains the motion. So above the frictional boundary layer, the pressure gradient and Coriolis forces can nearly balance. The wind then flows approximately parallel to the pressure or geopotential height contours. I hope this video could provide you good information, and see you in the next video.